of education. With that thought in mind, let us now begin our session. I take great pleasure in inviting Mr. Vijay Singh, first year coordinator, Department of Science and Humanities, to welcome our today's speaker, Dr. S. Kiraba. Welcome you, sir.
Am I audible?
Yes, sir, you're audible.
Okay. Good evening, everyone. Welcome to the second day of the faculty development program titled Advancement and Application of Smart Materials in Environment and Technologies, conducted by the Department of Science and Humanities of Marthandam College of Engineering and Technology. Now, I'm very happy to introduce the first resource person of the day two, Dr. S. Kirupa, Professor, Department of Physics from St. Joseph College of Engineering, Chennai. A teacher with 25 years of experience, she earlier worked at Bharat Nickton Engineering College and Banari Amman Institute of Technology. As far as her education is concerned, she completed her doctorate degree in the field of medical physics from Anna University, Chennai. She has published 18th international journals and published 8 patents. She has been involved in NPTEL and AICT courses as well. Further, she has been involved in funding project and already submitted a COPA project funded by SCRB CRG. It is a core research grant paper with an amount of nearly 5 lakhs. A fitness enthusiast as well as a social activist. Her hobbies are photography and listening to music. Beside her education, he is a well fluency in English, Tamil, Telugu, and Bagda. With immense pleasure, now I like to invite Dr. Kiruba to give a talk on the topic environmental and health impact of earth materials. Welcome you, ma'am.
Thank you, sir. Thank you very much. So good evening, everyone present here. I'm Dr. Kripa. I'm working in St. Joseph College of Engineering. Thank you, Dr. Vijay sir, for your beautiful introduction. I'm really thankful to the Almighty and also to the chairman of both the institutions, St. Joseph Group of Institutions and Marthandam College of Engineering, as well as my heartful congratulations for the coordinators, because it is not an easy thing to conduct this FDP, that to an online mode. We will be able to hear the virtual reality, but all the people in this online, we are going to experience that virtual reality for for some time. So my topic is, can I share the slide?
Yes, ma'am.
Is it visible, ma'am?
Yes, ma'am, it is visible, ma'am.
So my topic is on environmental and health impacts of earth materials. When you see that environmental and health impacts, everyone, we will be thinking about the pollution and the impact of pollution on the people. So we will be able to know well about the soil pollution, water pollution, air pollution, and land pollution. Even nowadays, gadgets are becoming as pollution because it creates a great negative impact on us. And we are able to know the causes of pollution and also the measurement taken to eradicate the pollution. So all these topics are well-known topics and we have heard a lot of lecture regarding this. But in today's lecture, we are going to see something different. So environmental, just to replace this word by your name. For example, Kripa. So Kripa and health impacts of earth materials. So what are the earth health impacts of earth materials on me, both as merit as well as a demerit thing? So for that, we want to see something in the beginning. We want to see what is earth material. Only then we can get inside the detailed lecture. And I like to connect you with the research, what I was doing, and I'm doing that. So the earth materials, we know that it consists of sediments. So these are earth materials. It consists of sediments, ores, rocks, petroleum, and minerals and everything. But all together have combined and gives us a natural material such as these four: minerals, rocks, soil, and water. We have heard about that is we all people are in comfort zone now. Without digital cameras, we are not there. Without flat screen TVs, we have the electronic displays, we have the monitors, hard drives. We see the sonar connections and also the biosensor connections, electric vehicles, smartphones, hybrid vehicles, and so many things. Can whether we thought what is the root, what is the base of all this, we can simply say that it is a man fabricated materials. All the sensors and everything are the man fabricated by man, human, and we are using that. But we forget about the past, we forget about the basics. We come to the designing part and also the implementation part, but we didn't go for the basic part. So all these materials come from earth only, so they are called as rare earth materials. So the earth is a mother who gives all these materials, and we are utilizing it. We are fabricating according to our taste, and that is applied to some in different fields. So now in for few minutes and few that is I think for 30 minutes or 40 minutes, we are going to speak about, we are going to I'm going to share the thought about the rare earth materials. In universal, there are only 17 types of rare earth elements. Even though the earth materials are minerals, rocks, soil, and water, all these four earth materials have given rise to 17 types of rare earth elements. Being a physicist, we are calling that as advanced engineering materials, or even very rare materials and everything. We have heard about what is that, shape memory alloy, and so many things, so many engineering materials we have come across. And on what basis, what is the base of the production of that shape memory alloy? So that we are going to see for a few minutes. So there are 17 types of rare earth elements. And the first one, if you see, that is of scandium. So first is of scandium, and it is of yttrium. So many things are there. Um, just a minute. Just a minute. There is a call. Just a minute. Sorry. Thank you for your patience. So scandium, yttrium, lanthanum, cerium, praseodymium, neodymium. So I think among these seven, I will go through that. Promethium, samarium, europium, galadonium, terbium, dysprosium, holmium, arabium, thulium, ytterbium, and lutetium. I think all the words are very difficult to be pronounced. In all, among the 17 rare earth elements, I think we have come across only neodymium alone. Because as a physicist, we have that neodymium laser as one of the part in engineering physics, what we are teaching for engineering students. So the neodymium laser, it is a glass laser which can be used to eradicate the eye surgery and everything. It is ruling in the meritorious part. So these seven types are the product of this four earth elements. The man has fabricated and they have combined and they have made so many mixtures of these 17 types of rare earth elements, and so many other elements have been produced. So now we are going to see what is this, what is the earth material, minerals, rock, soil, and water. One thing we should remember that here the minerals are used, they are not as per used in nutritional labels and pharmaceutical products. Because in pharmaceutical products and nutrition labels, minerals will be there, but that mineral is not the same as this mineral. This is something, this means in a geological sense, because from school days onwards, we have studied the geography. I don't know how far, how many people we have been drawn towards the geography, but I was very weak in geography. But after I took my PhD research in the archaeological samples, that is in medical physics, I was really attracted towards this geological factor. So really this mineral is in the geological sense. So here the mineral is nothing but a substance which occurs naturally, and also the substance which is inorganic, as well as the substance which is a solid at room temperature, and also a substance which has an orderly and repeated crystalline structure. Beyond this, it has a chemical composition that can be defined by a chemical formula. This is a mineral. This is a mineral. For example, if I want to say water and mercury are minerals, but we don't call that water and mercury as minerals. We'll be calling that as liquids. Colloquially, we will be calling that mercury and water as liquids and not as minerals, but actually they are minerals. But when we call the CaCO3, that is calcite, it is a mineral. We will be calling that calcite as a mineral. So all this depends on our mindset. By seeing our mindset, the International Mineralogical Association, they gave a prompt definition for this mineral. So it's an element. It's an element which is a crystalline in nature and also formed as a result of geological processes. So because of this, the mineral has been formed. And when you come across this pearl, opal, amber, and everything, they are also mineral, but not a prompt mineral. They will be, they don't have crystalline structure. So they will be called as mineraloids. Why I'm insisting this means the next coming rock, this rock is a solid substance which are made up of one or more mineraloids or even minerals, but mineraloids will be more than the minerals. So the rocks, the building block of rocks is nothing but mineraloids. So we know that there are three, just a minute. So we have to thank the earth because the earth has a large number of, I think, spheres, not only sorry, materials, but also spheres. And one thing beyond everyone, we have to thank the geologist, because without that geologist, we would have not invented all these materials at all. The geologists are the people who view the earth as an operational system. For them, the earth is an operational system of integrating the spheres. I think this diagram can show the integrating sphere part. So here you can see the lithosphere, geosphere, atmosphere, hydrosphere, biosphere, and everything. All the spheres are the OS, operating system for the geologist. We know that geosphere is nothing but the solid body of the earth. And when you come to the atmosphere, it is full of gas envelope. It will be surrounding the earth. When you come for the hydrosphere, it is of water found everywhere at and near the surface of the earth. And when you go for the biosphere, it is nothing but the life on the earth, including the human kind. And one more sphere is there, chirosphere. I think we have forgotten that chirosphere, that is a frozen part, that is fossils will be there, water will be freezed. It is a frozen part of the earth. So this lithosphere includes both the crust and the uppermost portion of the mantle, that is a solid mantle. This layer is a main part to talk about the tectonic plates. So the Mother Earth, it has undergone so many disturbances by the natural calamities, and it has a formation of different rocks and everything. So that rocks have given so many minerals to us, which we are using and which we are fabricating and which we are tuning according to our taste. So next is soil. So we have seen the minerals. The next is soil. We know that soil is another part of Earth's materials. How the soil is formed? It's a combination of broken down minerals, because the first is the hero for all the remaining three. So the soil is nothing but the broken down minerals and rocks and decomposed organic matter. So the broken down minerals and rocks are created when larger minerals and rocks are built into small pieces. So how it becomes a small piece? Due to the weathering condition or due to the erosion happening. So all these are a part of solid. This forms the soil. Water, I think it's the most wanted element of the Earth's material. It's widely used to make several different kinds of materials. So without these four materials, Earth is zero. And also the human life is also zero. Only from this minerals, rock, soil, and water, we are able to frame so many rare earth elements, and we are going for the higher advantages and application-oriented things. Now, what are the minerals which we'll be able to see in the, sorry, just a minute. So the rock forming minerals, there are so many formation of minerals. So mainly there will be only some 8 minerals will be seen in this earth. That is along with this, they are magnesium, sodium, potassium, calcium, iron, aluminum, and silicates, and also calcites will be there. But what about this big 10? This Big Ten is coming from magma. I think we all know volcano, and the lava which comes out is called as magma. It is a hot molten material. From that, all these Big Ten minerals can be extracted. Only from this Big Ten materials, all the other materials are developed. For example, I think we can go to the next one, rock. So in rocks, there are 3 types of rocks: igneous, sedimentary, and metamorphic. So we will see one by one. So I think you have seen the picture of this igneous rock. So many examples are there for igneous: kimberlite, granite, habro, basalt, pumic. So among all these rocks, among all these substances, I can give some examples. That is the health impact of some materials of igneous rock. I cannot say everything because I'll be running out of time. So first, for example, first you take kimberlite. This kimberlite, we will be surprised that they are the rock which often contains diamond. So in South Africa, you can find this kimberlite in surplus quantity. So it is the one and only rock which has diamond in it. So think about the diamond mine workers. Really, they'll be in a terrible risk because when they cut this rock and take, automatically they'll be suffering from the lung oriented diseases, the respiratory issues, and other health problems because they are highly toxic. The dust inhalation will be there, and almost several hazards they will be able to undergo. So this is of kimberlite from here. Next, at the same time, you see this by there is a proverb: by having a knife, we can cut an apple as well as our hand. Similarly, the kimberlite, even though it consists of diamonds, it creates some respiratory problems for the people who are dealing with it. Take this pumic stones. I think everyone, ordinary human being, will be using this pumic stones because it is highly beneficial, and also it will be used for exfoliating the skins. So the skin will become plumpish. But there are so many health risks also because overuse of that will lead to skin irritation, cuts, and infections, which leads to terrible diseases. So the pumic stone is used by humankind But kimberlite, after the refinement and everything, as a diamond we are using. But before getting that diamond, we have to undergo a lot of health issues, and also the hazard health impacts from that we have to face it. This comes from igneous rocks. These are the negative point, demerits. But later I'll come to the meritorious point of all these rocks also. Next comes sedimentary rocks. Here, sedimentary rocks, the most wanted, that is chalk is there, sandstone, iron, anthracite, so many things are there. But common, very common are chalk and sandstone. So sandstone, I think it is used for the construction purpose. The mining and processing can create a significant health risk because the silica is present in it. It is also produces dust, and inhaling the dust, definitely respiratory problems will be occurring, like silicosis and tuberculosis are the main causes behind this. And a long time exposure alone will be leading to this, but short time will never affect our health. It is used in construction, landscaping, and also in decorative element, the sandstone. And chalk, we know that it's used for so many purposes. Coming for the metamorphic rocks, it's very interesting here, metamorphic rocks. Before this, I think, yeah. See here, the granite. Granite is there, jadeite is there, and marble is also there. So all the merits and demerits have lied in a single rock. Think about that granite. Without this, just a minute. See here, in igneous rock, there is a granite. This is garnet and this is granite. So by using the granite, nowadays, even a small house have the granite countertops and also the granite floors. If you are constructing any houses or anything, the royalness will be shown only by this granite countertops and granite tiles and everything. They contain the radioactive elements. Granite contains the radioactive elements like uranium, thorium, and potassium 40. When you walk in the granite tiled houses with bare foot, automatically you'll be able to get that leg pain. I think some people have wondered why I'm getting the leg is paining for me, and my leg is becoming so weak. The main cause is the flooring. That is, if it is of granite, definitely it will be a health issue problem because it emits radon gas. Without our knowledge, the granite, it emits a radon gas, which can seep into the homes, particularly from the soil beneath the foundation. So from the underground, from the foundation, automatically it seeps into the homes. So when you keep a contact, when the leg and that is in contact, automatically the gas enters your body. So it leads to the risk of lung cancer. So nowadays we are hearing the word cancer frequently. They don't smoke, they don't drink, they don't even use tobacco or even coffee and tea, they don't drink, but they will be affected by cancer. If you see the root cause of everything, somewhere else something like this would have been connected. So the granite, it plays a major role for the lung cancer, and without the knowledge of that, we are dealing with that in our everyday life. We are thinking the granite will show our royalness, but automatically it reduces our life factor. So the radon, but nowadays EPA, Environmental Protection Agency is there, and they will be used to checking this measure. They'll use to check the strength of that radon gas. If the radon gas is, they have some numerical value. If that the radon gas obeys within that numerical value, no problem for that house. But even though some little bit harm will be there, the one and only solution for this is proper ventilation. So proper adequate ventilation in homes, especially in basement, because we use granite mostly in the tiles than in the countertops. So especially in the basements and areas with granite countertops, if the adequate ventilation is there, then it is helpful to dissipate that radon gas. Easily it will be dissipated. So this is one of the history behind this granite. And when you're coming for jadeite, Jade rollers, I think we are quite common about that. Really, I use this. I use this, and so many people will be using this. It's a type of jade. It will be in green in color, not even a nice green in color, Ramar Pachai. In Tamil, they used to say that. So it will be in that in color. So it's believed to offer various health benefits. Main thing, it promotes the physical and emotional well-being. It's a jade roller. It is available in markets. One thing, the main medical thing behind this, it reduces the puffiness. So since the age increases, we used to have some puffiness or the drawn skin, everything under the eyes and chin, cheek, everything. So in order to lift it up, in order to reduce the puffiness, you can use the jade roller. And this marble is, sorry, this rock is highly helpful in it. It promotes the blood circulation also. And also it helps to regulate the heart rhythm. So heart rhythmic, it will be regulating one by using the jade. It balances the energies. It reduces the stress. So for cardiovascular health, this jade is highly useful. So even the doctors, I think they'll be having the jade roller, but they will not be having the jade roller type, but they'll be having this stone. I think so many people would have seen as a paperweight. So many doctors would have had this jade as a paperweight there because it's highly connected with the emotional things. So these are the history behind the rocks, metamorphic rock, igneous rock, and sedimentary rocks. Now, can you guess what is this? So I think so many potteries are there and so many things are there. I know everyone can wonder what is this, why, what is the need of this. So my research work, so far we have seen the earth materials. Now my research work, we are going to discuss about the research work, what I was interested and in which I pursued my PhD. So this is nothing but pottery. We used to hear that the cooking in pottery and eating in the pottery extends our lifespan. Even our ancestors, they don't have any plastic or steel or any metallic utensils in those periods. They had only choices pottery. So they make the pottery with the different kinds of sand. So we are going to see some informations regarding that. So this pottery, it's nothing but a clay mineral. So it's a clay mineral and all these minerals will be sufficiently present in it. Silica, alumina, potassium, sodium, calcium, everything will be present in it. Now, what is the need of this pottery? Why pottery is important? The shape of the vessels, when you see the picture, I think you'll be able to get it. See here? We used to get the pottery samples only in this form. So from this broken pieces of the pottery, we have to determine that, okay, this is of neck piece. So this is a neck piece of that vessel, and these are some of the body parts. So I have excavated so many places. I have excavated so many places. I'll come back to that. But before that, we have to see what is the need of this pottery, because the need of this pottery is it speaks about the history, it connects the culture. So the shapes of the vessel and the modes of decoration change through the time, and pottery can be used to understand the periods during which a site was occupied. So really each and every period, each group will be using a different kind of potteries. Romans were the first people to introduce this pottery, followed then then Chinese people followed that. After the Japanese people followed it, and still now the China and Japan are using this pottery in the form of ceramics. But I think we have come out of that. We have come out of that, and we are thrown towards the plastic containers and everything. So we used to, in those times, the potteries were used to cook. They used to store food and also to store water and store oil and everything. So pottery is often the most abundant type of artifact. So artifact is nothing but the residues. There are so many artifacts. There are coins. See here. So there are coins, ornaments, bones and teeth of the animals or even of human. Weapons will be there. Potteries are there. But I have chosen the pottery because it is a significant sample. It is a significant sample, and we will be able to know the levels of the society lived in the past. But coins and ornaments also will define it. But even the coins and ornaments will not be there with the normal people. Only the royal people will be having that coins and ornaments. So from that we will not be able to study anything about the society which was living at that period. But the pottery will reveal everything. So the analysis of prehistoric ceramics, that is the pottery, will allow the archaeologists to find the cultural sequences and reconstruct the daily life, investigate the patterns of long distance exchange, because in those days, pottery was one of the exchange, trade exchange in those periods. And they will be able to identify the vessel form, function, and designs, and also the manufacturing technologies used at that time. They used to conclude in which part what manufacturing technology is used, so that the potteries will be different in shape. Some potteries will be very narrow, and some potteries will be wide, and some potteries will be designed with some paints and everything, which are man-made one, which has been taken from the sap of some trees. So, so they'll be able to get the quantitative record of that people attributes, and also the comparison was done. So in this place, pottery is like that. In that place, the pottery is like that. So the people involved in this place using this pottery were living a long life. But these people were suffering from some diseases. So what is wrong in that pottery, and what is wrong about the sand particles present in that place? So they came to the conclusion like that. So by using the dating, carbon dating, we used to find out the history behind that pottery samples. So I took the help of IG Care, and we took they provided me all the necessary instruments available for carbon dating, and I was able to find the period of that potteries. So now I think we can go into this. So archaeology is a scientific study of past cultures. Really, it speaks more about the lifestyle of the people who lived in those days. For example, Mayans. I don't know how many people have heard about Mayans. Mayans were the people who were they were the people they were the people who were first to introduce the aeroplanes in the form of drawing. So only by seeing their drawing, the aeroplanes and everything was designed. So the Mayans will be playing they play a great impact in our aeroplane designing and everything. So here, so pottery made of clay is so main thing. Pottery is mainly clay, and we will be seeing the compositions of the clay in the coming um, slides. So pottery made of clay is permanently hardened by firing. So definitely firing helps the pottery to become stable. So the nature and the type of pottery is determined by the composition of the clay, the way it is prepared, and the temperature at which it is fired, and the glasses used. Glasses means the polishes, the polishing nature. So first you have to determine the composition of the clay. What does the clay made up of? The composition of the clay, the way it is prepared, because you can prepare the pottery by two means. One is handmade, another is wheel made. We'll be able to identify or distinguish the pottery samples by seeing that itself, because we have the experience. But those who are freshers to see the pottery, they'll not be able to identify whether it is a man-made, that is a handmade, or a wheel-made, because in those days the Romans used only the handmade. But Chinese, who came along with the Romans in the pottery era, they invented this wheel. where the clay will be kept and the wheel will be rotated and the pottery will be made. So they were the first person to create an innovation in the pottery samples. So these are some of the sites which I have preferred, which I have excavated. Vallimalai, Thiruverkadu, Kaveri Pakam, Panchapandavar Malai, Ooty, that is Udagamandalam, and Pumbuhar. So all these are some very historical places. Very historical places. There are so many historical places. Even Sangari, Drug, and so many places are there. But pottery samples, we cannot go and dig it because already the archaeologists will be there, and only with the permission of them we can get some samples. They will be digging, and with the permission of them we can have some samples, and we can have that in our physics mode, because they will be doing in some other study, but we can apply some physics method of studying in that pottery samples. So I have used the carbon dating and everything, but before that we have to get a little bit a detailed study of this pottery samples. So the first one, you have to locate it. The latitude and the longitude plays a vital role, because some will be very close to the shore, coastal shore, like Pumbuhar. Pumbuhar is a coastal area. But when you compare that to the Udagamandalam, it is a hilly region. It's a hilly region, and we know that all the people have been spreaded. Um, they have been spreaded and they have lived their own life, and whatever the materials available in that spot, they used to convert into their usage. So I have taken so many different types. Thiruverkadu, it is a normal place. Thiruverkadu, Kaveri Pakam, or normal place. But this Panchapandavar Malai, Valli Malai, Udagamandalam, there will be somewhat hilly regions. Udagamandalam is a high hilly region, but comparing to this, the Valli Malai and Panchapandavar Malai is a little bit one. So hilly region, but this Pumbuhar is of coastal area. So what differs in this? Why I have taken normal plain, like a little hilly and high hilly regions, and also a coastal region. So by comparing all this, you can come out of the results. So I have got the samples only from the ancient history of archaeology. There is University of Madras, because without their help, I would have not finished my research. So University of Madras, and also Government Museum here in Vellore and Chennai, they helped me a lot. So these are some of the photographs of the pottery samples from Thiruverkadu. So after getting this, you have to identify this. You have to identify, and we know that this is a neck part, and this is a basement, and this is a body, and this is very close to the neck part and everything. And we know that these pieces are not from one pottery sample. They are from many pottery samples. So you have to identify the dating. That is, you have to identify the lifespan of each pottery sample. So everything was red in color. I think if you have noted the color of the pottery samples, everything is of red color. See, red slipped ware. And also you have to write the identification of that. It was very polished. Surfaces were highly polished, and you want to measure the thickness also, because the thickness, the manufacturing system and the designs on it, everything talks about the era. Everything it talks about the history of that, and also the period of that pottery. Now coming here to the next one, this is of Kaveri Pakam. This Kaveri Pakam, I think you can see the difference in the colors of the pottery samples. That was a red in color, but this is completely dark. These two samples are dark black, and this is somewhat a combination of black and brown. This is of black and brown. So this black and brown, when I come to have this in Japan, I think how many people have heard about Joban potteries? It will be like a face like pottery. Human's face like pottery will be there, and the kings will be used to drink wine, and drinks will be supplied in that. So that is called as Joban. It will be both in the combination of this brown and black color, because if the brown color is there or black color is there, we know that from the beginning itself, I told that the earth materials have 8 essential minerals. 8 essential minerals: magnesium, potassium, sodium, calcium, iron. So iron will be the main content in that, but not iron will be not be the main content, one of the content, but silicates will be main. But this iron, when it is present in red in color, they will be called as hematite. And when they are black in the black in color, they will be called as magnetite. So see the versions of their names. A simple compound iron, they have been classified as hematite and magnetite. The same thing, sodium, the natural mineral sodium which are found in earth's crust, when they combine with chlorine, we will be getting sodium chloride. So normally it is a table salt, but what is the mineralogical name for that? It is halite. So the name of that is halite. That's nothing but the table salt, which we use in our daily life in food and everything. So there are some mineralogical terms. So iron will be called as hematite and magnetite. So this indicates that Kaveri Pakam potteries, that the sand used to make the potteries in this Kaveri Pakam zone have a rich content of iron. So think about the people, the health of the people. Definitely, the no iron deficiency would have been there for the human who have survived there. So the next one is, you see here, this is Panja Pandavar Malai. Here, both the combinations are there. A red color, red ware is there, as well as black ware is there. So here the soil has black and red. So this means it is not a local soil, it is an imported soil. So somewhere the soil has been taken and it has been come and they have made the pottery, or some people from some area already they have made some pottery and they have been shifted to this place by carrying that pottery. So in one place only one nature of soil will be available. No different soils will be available, either black or red. No black and red will be available in the same territory. So here this means the Panchapandavar Malai in this place, I think so many nomads were there. So many nomads who came from various places, and for the survival purpose, I think they would have settled there. So the black color pottery was there, and red color pottery also was there. So the sand consists of both. The sand consists of both, or we have to take like this. The sand is of only single form. A little bit of variation of soil mix with that. So this is of Panchapandavar Malai's history. When you come here, the same thing happens in Valli Malai. So the Valli Malai, Panchapandavar Malai, everything is of nearby hilly regions. So I think so many transactions were there done by the people. Here, the people were moving from this Malai to that Malai and that Malai to this Malai, I think. So only so the combinations of hematite and magnetite were found here. So the last one is Pumbuhar. Pumbuhar, we know that it's a coastal area. So coastal area, see here, everything is of red in color. So hematite is a dominant one. So magnetite will not be there. When you come for the Udaga Mandalam, similarly here it is a combination of black and red. So I think Udaga Mandalam, it is very close to Karnataka and Kerala and Tamil Nadu. It meets all the three states. So the people would have been migrated. The people would have been migrated from one place carrying their own accessories and everything, utensils and everything. So here, at last, comparing all the five, the natural clay, the natural soil exists in Pumbuhar and in here in the, what is this, Kaveri Pakam and Thiruverkadu. So these are nothing but the local sands. They are not the imported sands. They are not the migrated sand. They are nothing but the local sands. So from these three places, I have discovered so many informations. I like to share all that. So first is of infra. Let me go to the first slide. So what is the objective of this? So what is the objective of finding all this clay mineral? So how can you find this? How can you find the clay minerals? Because the clay is not one compound. there will be sand, there will be slit, so many things. So how can you identify that? Only by using the FT spectroscopy. So FTIR spectroscopy, you'll be able to identify the different compositions of that clay. And by using the same FTIR spectroscopy, you'll be able to find out the temperature, at what temperature the clay would have been heated and converted into a stable pottery. And also I have used micro-Raman spectroscopy to confirm it. So it's an additional spectroscopy method which was used to confirm the presence of the minerals there. And porosity measurement, this is very interesting one, porosity measurement, because it's a very simple method. It's very simple method and a simple instrument to find that is available. What is the need of this means? In those days, the pottery samples were used to store solid food as well as a liquid food. For example, water and oil as a liquid food. In solid food, cereals, pulses, and so many have been stored. So the pottery which were used to store the cereals and pulses, we don't bother about the porosity, because the pottery will never absorb that cereals or pulses. But the pottery which is able to store the water and oil and liquid form, any liquid form, definitely we have to concentrate on the porous nature of that pottery samples. If not, it will absorb everything. It will absorb everything. Even in our daily life, when you are very new, you are a new user of a pottery sample, we will be able to immerse that pottery samples inside the water for 1 or 2 days, because all the open pores will get compact. There will be a closeness between the substances so that they'll not be able to absorb the oil or anything. So the same thing here. So you have to measure the porosity of the pottery samples. It's highly essential. The next instrument I used was SEM. So because the SEM, it gives the minerals which we were not able to predict from the transform spectroscopy, that is FTIR spectroscopy. We'll be able to get so many minerals. Mineralogical study can be done with the SEM. And the last one was chemical analysis. So that is a confirmation study for that. So all this methodology we can use. So as a physicist, we have been concentrating in so many ideas, so many fields. But I think this archaeological field also we have to concentrate. We will be able to know about the earth, and also because beyond, apart from the physicist, nobody else can link hands with the geologist. So the geologists are the people who give the materials to us. But we, the physicists, are the materials who will be able to study that and take to the higher level. So if, I think everyone, you have to think about this. Why can't you connect the archaeology with physics? So I think this is a new technique we have followed. Not only potteries, but I also have studied about the sediments also. Sediments which were available in ocean. So I have taken the Bay of Bengal ocean, and we would have collected the sediments from there. And we have splitted all that into sand, slit, and everything, waste particles, everything has been splitted. And whatever the methodology applied for pottery, I have applied for the sediments also. Because when you take the coastal line of this Chennai, it goes from Chennai to Kanyakumari. And so many well-known organizations are there, even IG Care, everything is there, Kalpakam. So the river, the water near that IG Care and everything, so many radioactive pollutant will be there. The living organisms will not be able to survive in it. So when you take the sediment and you have a study about that sediment, you'll be getting all the informations about it. How much percentage of arsenic is there, how much percentage of toxic elements are present, only because due to that, the living organism, the aquatic living organisms are not able to survive in it. Everything you can predict from that. So not only potteries, but also in sediments, we can switch over the concentration. Now coming to the main thing. So, so the pottery, it does not only gives a culture, it speaks the culture and also relates the people. There will be a therapeutic value. It's a medical, the pottery will bring a medical value into our life. because in the 1940s and 50s, where the medical field was not well established, they believed only on nature. The curing comes from only on nature. So the pottery was really a great, it made a great impact. There was an art called as clay art therapy. In China, they'll be called as cat, clay art therapy, because when you make that potteries, you will be able to, you'll be having a mindfulness. When you make the pottery, all your senses will be engaged and your attention will be focused only on that activity alone. So the mind, everything will be very quiet and you can reduce your stress and everything. So making a pottery is a really an emotional therapy. It's a behavioral therapy. Only so in China and Japan, when you are under stress, you will be asked to go for this cat. And also you'll be asked to go for that CBT, that is cognitive behavior therapy, which is involved in the pottery making. So the pottery making for us, roughly it will be of pottery making, but see how the people have turned that into an art-like structure. So now coming to the main thing, the history of clay. So the history of clay, at almost basic level, clay is nothing but a earth material, where the minerals, you can trace some minerals, or you can trace some metal oxides or organic matter and everything. But beyond that, the primary minerals in clay are kaolinite. So kaolinite, which is roughly they are called as kaolin. I think we have so many cosmetic items nowadays. We are using so many cosmetic items, serums and so many lotions and everything. If you see the ingredient, one of the ingredient or composition in that will be of kaolin. So this kaolinite it plays a major role in this. So I think I can give a detailed description about this kaolinite. So it's a clay mineral. It's a clay mineral which is very important, and it plays a major application across various industries. It is that is a key ingredient for the ceramics. For ceramics, not only for ceramics, but also for paper production and pharmaceutical. And also it is used in agriculture and cosmetics also. For example, when you come for ceramics, they are the primary compound. They are the primary component in porcelain, earthenware, because the potteries are classified into three types. One is of, I think I have that picture, or I don't know that. If time permits you, please, you can Google it and see. Potteries are classified into three types. One is earthenware, stoneware, and porcelain. So these are the three types of the potteries. Earthenware, the material which we get from earth, by having that we'll be making a pottery. Stone, we know that from rocks you'll be making the pottery. And porcelain, it is a man-made, it is a fabricated pottery. So that is the latest technology. Porcelain means nothing but ceramics, and that is the latest technology here. So in ceramics, the kaolinite is a primary component because they are more strong, and also it can be molded. Even though they are strong, they are highly flexible. They are highly flexible. So here comes one of the new engineering material. So I think we have heard about metallic glasses. Metal will be crystalline, glass will be amorphous, but combining both with the help of some new engineering technique, both the crystalline and amorphous have been blended together. Similarly, here the ceramics will be strong enough, but they can be easily molded. And when you come to the paper technology, that is in paper production, this kaolin, it will be acting as a coating. It will be acting as a coating and also filler. It will be filling that paper production, and because it enhances the brightness and printability will be more in that. And at the same time, this is used for paints and coatings also. Paint and coatings, the kaolite will improve the whiteness and the durability of the paints and coatings. Not only in paints and coatings, they are used in as a filler in rubber. So filler in rubber, they are used as adhesives and sealants. They are used in cosmetics. They are used for in face masks, soaps, and so many things. Cleansing material. It plays a major role. I think multani, that sand is there, no? The clay. Similar to that, this kaolin will be making some impact in our skin. So not only in these field, but also in pharmacy side also, this plays a major role because this kaolin is used in medications for digestive systems. If you have some stomach upsets or even diarrhea, by absorbing or by taking inside this kaolin, everything will be rectified. The gastrointestinal problem will be rectified by this mineral. Now you think about our ancestors who cooked and lived with the help of pottery. I think they have been survived to a long extent of life. More than 100 years and 120 years is quite common. Even if you take Japan or China people now, since they are using the ceramics, the pottery samples, their lifespan is excellent. In Japan and all, you can see so many people beyond 100 years and 120 years. I think this is one of the reason. This is one of the reason because they mingle with this. They mingle with this mineral content pottery elements. So in agriculture, this kaolin is used as a natural pest controller. So natural pest control, and also it removes the pollutants from the water and soil. So these are the main what is that merits of this kaolin. So this I was able to find in that the kaolinite, dictite, and nacrolite. So they have the OH stretching bonds. So when you use the FTIR and have the graph like this, I'll show that. So from this graph, if you have the OH bond in that particular absorbance intensity, then you can predict that kaolin is present in this. At the result, we can see among the 5 sites which have the high content of kaolin. So next to this is hydroxyl groups. No wonder to that, because in order to make a pottery, you are in need of water. So water should be mixed. So automatically the hydroxyl groups will be present in all the pottery samples. And this is of organic matter. Just like because the pottery samples will be rolled in the floor and everything. So some of the, all these are waste materials, we can say. Now coming to the silicate bands. So silicates will be present, and carbon will be there. Definitely carbon will be there. So I'm very glad to say that one of the pottery sample of the site which I have chosen had purpurite. So this pepperite, it is really one of the amazing thing. It will be blue in color. It will be in purple in color, and it is called as peridot. It is called as peridot, where the people who born in the month of August, they'll be having this gemstone. It is one of the gemstone. This pepperite is one of the gemstone, and the people who born in August will be wearing this. I think we have heard about that Rasi stones, no? That are the gemstones which will be used for that. So for that, they'll be using this because it creates more magnetic power inside us. And so because of that, innovative thinking will be more in this. So people from China and Japan, when you see the ring made, when you commonly, they'll be using this purple color. Purpurite, very rare, very, very rare earth mineral. Suppose if you are able to get 1 kg of this mineral, after the refinement, you'll be having only 1 gram of it. So such a peculiar and very costly mineral. So I'll say in which area I got this. So the purpurite, it will be having this. It increases the blood circulation also. Mainly blood circulation. It heals the wounds, and also the sunburn, acidity, stomach acidity, and reduces the heart palpitations. Nowadays, irrespective of the age, the palpitations are common for us. It is a common disease which has been occurred. Even the school going students are having that palpitations when they come across some stress. So this peptide. This peptide will be able to help us to come out of that. In Hinduism, they'll be calling this chakra healing. So the chakra healing, that is known as the third eye and so many things, crown chakra and so many factors they'll be saying. In Buddhism, these chakras will be completely followed. So when you visit Japan or China or the countries which are associated with that, even in Bali and these things, you'll be having this purple, that is pepperite mineral, a small, what is that, a small rock shaped, or even a Buddha will be made of pepperite, and that will be at the temple. You can see that temple, and if you inquire about that, the guides used to say that it is made up of some gemstone. But as an archaeologist and a physicist, we will be able to know that that is made up of pepperite, which gives the emotional well-being to us. So the next one is quartz. Yeah, quartz, really interested one. And everybody, we know that quartz, it has so many medical benefits. Medical benefits both in alternative and traditional medicine. It promotes the physical healing. It balances the emotional thing and also the spiritual well-being, everything. Because even those who are highly spiritual, you have seen the quartz jabamala in their neck. They used to carry this, even Christians or Muslim, irrespective of the religion, they'll be having some malas in their hand or in the neck. That is purely of quartz. So quartz, I think it balances the energy flow in our body. It releases, it makes us to come out from insomnia. And even the cardiovascular issues are rectified by it. Mainly the quartz are used for pain relief. If there is a headache or muscle pain or anything else, and also it reduces the inflammations also, the quartz. So bone healing also can be done by the quartz. So many meritorious things are found in quartz. So these are the secondary mineral. The first mineral or the kaolin, dictite, purpurite and everything. The secondary mineral which we are able to find from the potteries are, one is quartz. So it reduces the stress also. It reduces the stress. So they are used in electrotherapy, medications, and feng shui. So if you come across the practices which are quite common in Japan, China, and Thailand and everything, it is of feng shui is a method where they used to give the massage using the quartz stones. Or even the magnetic pebbles will be used to give the massages for them and will be relieved from that. All types of pains. So this is the importance behind the quartz. The next is accessory minerals. First is primary, the second is secondary. The last one is accessory minerals. Here there are so many things. That is manganese oxide is there, and calcite. Calcite is a quite common thing, no? Excuse me. So calcite, it is found everywhere. Going to the next part, yes, here. So albite, microlin, muscovite, all these are accessory materials. Each and every material, they have their own advantages. They have their own merits. When you see the microlin, it is a feldspar. It is a potassium-rich feldspar. It is both used in industrial purposes as well as in natural geological purposes also. They play the major role. They are nothing but ceramics and glass. In porcelain, ceramics, glass, a little bit of microlin will be there. Microlin will be there because it is nothing but a potassium. So when the body gets a deficiency in potassium, automatically some diseases will be there in our body. So that can be enriched by this microlin material. So it's also in so many nowadays in so many countries they are considered as one of the gemstone. Amazonite. The name of the gemstone which is made up of microlin is called as amazonite, which will be a green in color, and they are able to wear that nowadays. So the next is called as muscovite. Muscovite, it is a typical mica mineral. So we know that mica, it is an insulator. So mica, it is a typical mica mineral, And also it offers both the practical and metaphysical benefits. It also used in industrial applications also for insulation, paints, cosmetics, and so many emotional balances, and not only industry but also in human lifestyle also it is used. Paintings and coatings, cosmetics, everywhere they are playing the major role here. And also they are used in what is that clarity. If there is some problem solving, or the organizing thoughts are lagging, the clear thinking is lagging, this muscovite plays a major role. So the stones, the impact of the real earth stones, I think only the eastern country people, they were able to know that, and they have all the stones within them. Muscovite stones will be, if you visit Japan or Bali or anywhere else, you can see all these stones, muscovite stone, purpleite stones, albite stones, all the stones will be available. When you are coming for the alphite also, it is also a feldspar family. So feldspar group, potassium rich, calcium rich, so many rich feldspar group is available here, and one among them is alphite. So they are used as a glass production. So they are used as a flux in glass production, and they are used to coat the pottery items. So the glassy nature of the and the mirror like the glassy nature and the mirror like pottery samples are got only by applying that albite mineral over them. So they are nothing but so these are the albite, microlin, micro muscovite, everything. Now coming to this hematite, magnetite, all these are iron content. All these are iron rich minerals. And we know that iron rich minerals, definitely they will be boosting our iron content, and also it increases a magnetic property in our body, which is highly essential, because only when the electromagnetic what is that electromagnetic energy is good in our physique, we don't get any diseases at all, we don't get any joint pains or any headaches or anything else. So if the electric EMF is reduced in our body content, automatically all the pains and everything will be attacking us. So that can be minimized by this hematite and magnetite materials. I think nowadays in Tamil Nadu or even in India, what is that maram or something, karuvali maram or something has come, no? So that is full of magnetite. That is full of magnetite, not hematite, because it's of black in color. So full of magnetite. So when it comes and touches our skin, either through the chain or the bracelet or some rings or anything, when they have a direct contact with our skin, it will implement the electromagnetic flux into our body. So the reduced flux will be compensated by that magnetite. So really it is a biomedicine. So biomedicine, because even yesterday we heard about a ma'am, she talked from Lila College, she talked so many things about biomaterials, and the coming session, the next sessions from tomorrow and the after tomorrow will be dealing with biosensors. So where does all this materials comes from? Biosensors, biomaterials, all are nothing but the high level applications, high level materials. But the root cause, the basics of all that biomaterials, biosensors, LEDs, whatever we are leading in our comfort zone, in our homes and everything, the basic material comes only from this rare earth materials. So among the rare earth materials, I have taken one portion, that is a pottery, and we are discussing that. So now coming to the next one. So these are the graphs which you used to get, and these are nothing but the vibrational assignments. So in this range, if you get this is present. So if we can, albite is present, muscovite is present, magnetite is present, you can conclude it. So even though there are so many number of samples I have traced from Thiruvedkadu, only these two samples and this sample, they have been muscovite is found. And this hematite and magnetite also, only in few samples it has been found. So the remaining samples, they don't have that. They don't have that. They can be a combination of some other things. So this is of Kaveri Pakam. So Kaveri Pakam spectra. So I think you can see the differences from FTIR. Yeah, now coming to this. So the Pumbuhar sample alone contains the primary mineral kaolin. So the coastal sample has more amount of kaolin. So when you go very close to the shore, you will be able to see some clay-like sand or black color glittering sands will be there. So the black color glittering sands very close to the shore indicates a number of radioactive elements in it. Radioactive like uranium, so many radioactive elements will be there in that sandy material. And this Pumbuha, since it's a coastal one, the clay material, kaolin is present in abundantly it is present. And when you are coming for Thiruverkadu, Kaveri Pakam, Valli Malai and Panchapandavar Malai, quartz is present. Quartz is natural. It will be present. I think wherever we go, we can come across the quartz. Only because of the surplus amount of quartz, the quartz is used in all applications. And in everything we are able to use the quartz. And next one is this calcite, manganese oxide, all are present in Kaveri Pakam, and this albite. So see here, the Pumbuhar perpetite is present in Pumbuhar. So from this, you can come to a conclusion that the clay particles or the clay materials which are used for the pottery samples, which are very close to the coastal area, will be having so many treasures. The coastal area sand and clay particles they are the treasures for us. You'll be having what is that, many perlite or microlens structures from the coastal sites. So it's very beautiful to see to that. So albite is present in Thiruverkadu, muscovite is present in all the trees. So from when you come across this Pumbugar coastal area, you can see the porphyrite, you can see the muscovite, and also you can see the kaolin. Everything, what are most important minerals you can find in the coastal regions. So you have to, suppose if you are able to do some research in this archaeology connected with the physics concept, you can collect the pottery samples or even the sediments, the coastal sediments, because they will be full of rich earth materials. So comparing to the iron compounds, when you're coming for the iron compounds, magnetite and hematite, I think they are present in Pumbuhar and this Thiruverkadu. Thiruverkadu and Pumbuhar, they are ultimately they are present. And without any doubt, you can say in the coastal areas, they'll be having tremendous treasures. So the chemical analysis, I think this is of some other things, and we will be using the NAA method for that. And so many fluxes will be found. So aluminum oxide fluxes and silica, alumina, and everything will be found here. So the last one is, I think we can come to the conclusion. Firing temperature. Because the pottery will not get complete until it is fired. So how much temperature you can use? What temperature you can use to heat the pottery? In which temperature the pottery becomes stable? So it can start from 500, it can go until 1100. We can see, have you heard about the Sulai bricklin places where the bricks will be heated? So the temperature, similarly, the pots will be heated from 500 to 1100. So within this, from 500 to 1100, some of the clay minerals which are very weak will be diminished. They will be negotiated. Only so, even though I have taken so many number of samples from 5 sites, only few samples reflected some rare minerals. Some particles, some broken potteries were not able to reflect the minerals because while heating, these minerals will be damaged. These minerals will be vanished. So I have heated in what temperature I have heated, the 550, 650, 750, the intervals of 10. You cannot continuously heat it. You have to give some gap and heat. You have to heat until 550, take away, cool it, analyze it, confirm the minerals present in it, and then go for 100 more degrees, take away, cool it, and confirm the minerals present it. So like this, you have to, for one sample, nearly you have to follow some 4 or nearly some even 10 hours are required to find out the minerals in different temperatures. Really, it is a great work. I think some people, if you are interested, you can contact me so that we can link our hands and we can do this job. So I think I have justified the time given to me. So we have seen a lot of rare earth materials. I think I didn't bore you. In the coming sessions, I think you'll be hearing much more interesting lectures than this. So I thank Marthandam Engineering College, the management of Marthandam Engineering College, and Dean Dr. Vijay Singh sir, and also the coordinators for your great effort. Thank you very much. Thank you, participants. If there is any doubt or any queries, you can post it, or even you can unmute and you can contact me.
Yes, now the session is open for questions.
So I think this talk would have been new to you. So because when we speak about the environment, automatically we go to the old concept like pollution, causes of pollution, measurement taken for that and everything. But I think this was new to you. So suppose if you have any different ideas also, you can contact me so that we can utilize it. So as a physicist, we are doing our research only in atomic physics or some other things. Why can't you connect? Why can't you come to the geology side also? So well and good. I think I have done my best. So if there are any queries, you can contact me through mail or even mobile number. You can get from the coordinators. Whether any metal oxide present, yes, of course, from FTIR, yes, you can detect it. You can detect the metal oxide. But one thing, after heating only, we can go for FTIR. So while heating, some oxides will be going off. So our motto is to find only the primary, secondary, and accessory minerals from the FTIR. We don't concentrate in oxides and all.
Yes, participants, is there any questions? You can ask in chat box or unmuting your audio, you can ask now.
So if there is any doubt or even if any collaboration needed, please contact me through mail so that I'm ready to help you. And also we can link our hands and extend our work towards this archaeology. So, okay, thank you. Thank you very much. Thank you very much, Abita ma'am and Anusha ma'am, for giving me this opportunity. Really, I'm grateful to you people and also to the management of Marthandam College of Engineering.
Okay, ma'am. Thank you, ma'am. Thank you so much. So,
Thank you.
on behalf of our institution, Marthandam College of Engineering and Technology, I extend my heartfelt thanks to our esteemed speaker, Dr. S. Kiruba, Professor of Physics, St. Joseph College of Engineering, for the enriching and insightful session on environmental and health impacts of earth materials delivered today. Your depth of knowledge, clarity of thought, and generosity in sharing your time with us reflect the true spirit of academic leadership. We are truly honored to have had the opportunity to learn from you. We appreciate the time and effort you dedicated to sharing your expertise with us. Once again, thank you so much, ma'am, for an inspiring contribution. Thank you so much, ma'am.
Thank you, ma'am. Thank you very much. And thank you, participants. Thank you.
Now, I call upon Dr. P.S. Abhita, Assistant Professor of Physics, Department of Science and Humanities, to welcome our next speaker, Dr. P. Tamilarasan.
Ma'am, am I audible?
Yes, ma'am, you are audible.
Good evening to all. It's my great privilege to introduce our esteemed chief guest, Dr. P. Tamilarasan, senior scientist and assistant professor at the Academy of Scientific and Innovative Research, Central Electrochemical Research Institute, Karaikudi, for session 2 of today's faculty development program titled Advancement and Applications of Smart Materials in Environment and Technologies. Dr. P. Tamilarasan is a distinguished researcher with expertise in electrolytic and electrocatalysis division. He has collaborated with several prestigious institutions, including IIT Madras, CSIR Sikri, and the King Abdullah University of Science and Technology, Saudi Arabia. His remarkable research contributions have resulted in more than 40 publications, patents, and book chapters, with several works highlighted by Nature India and other leading journals. He has also received the Best PhD Thesis Award in Energy Applications from IIT Madras, as well as the Invention Award from Intellectual Vendors. Apart from his pioneering research on nanomaterials, biosensors, supercapacitors, and renewable energy devices, Dr. P. Tamilarasan is deeply committed to nurturing young scientists. He has successfully guided many doctoral and postgraduate students in their academic journey. We are truly honored to have such a distinguished scholar with us today. I now request Dr. P. Tamilarasan sir to kindly take over the session and share his valuable insights with us. Welcome you, sir.
நான் இப்போ ஜஸ்ட் இங்கே பேசினேன். எனக்கு ஐ டோன்ட் நோ என்னோட ஆடியோ அங்கே வருதான்னு தெரியல. சாரி, இல்லை நான் ஆடியோ செக் பண்ணிக்கிறேன். நீங்களோட இதில் ஆன்லைனில் வாங்க. ஓகே, சரி. பட் எனக்கு எந்த ஆடியோவும் வரலைங்களே. ஓகே,
Sir, can you hear us? Hello? Sir? Sir, can you hear me? Hello? Sir, hello? Sir, can you hear you? Hello? Sir, can you hear me?
ஹலோ.
Yes, sir, we can hear you. Hello?
ஹலோ.
Hello?
Ma'am, am I audible?
Yes, sir, we can hear your voice, sir. Yes, sir, you're audible now.
Ma'am, but உங்க ஆடியோ எனக்கு வரவே இல்லை.
Oh. But your voice is audible. Good evening, sir. Can you hear us
Yes,
now?
ma'am. Yes, ma'am. Yes, ma'am.
Okay.
I think something wrong with my my audio, but it was fine with MS Teams even today.
Okay, sir. Thank you, sir.
Fine.
We have.
Yeah.
We have.
Shall we start with my presentation, or you have?
Yes, sir. We have introduced you already, so you can start.
That's absolutely fine. So we have 3 more minutes. Should we wait for someone, or we can start?
We can start, sir. It's okay. It is okay now.
All right.
Okay, sir. Thank you.
I'll just up my slide.
Okay, sir.
Okay. Is it there?
Yes, sir. Yes, sir. I can see your screen, sir, now.
So now it's changing, right?
Yes, sir. Yes, sir.
All right. Okay. So I welcome all of you for this second session of this day. And after some technical struggle, I hope I'm with you now. I hope they introduced my name as well. So I'm Dr. Tamilarsan from CSR Supri, working as a principal scientist. And my work here is on 2 major verticals. One is on operando spectroscopy, another one is on microfabrication of devices like OECTs. So just to start with, this is my, I believe always this is my responsibility to thank Sir Valla for donating us this institute, and it has its own history. The institute was established in 1948 with the philanthropic thoughts of Sir Valla, and the institute is located close to Madurai, one side, and the other side Tanjavur, and another side we have Rameshwaram. So it is centered between these 3 spiritual cities, and it is around 300 to 350 kilometers from Marthandam. And if you see our campus, it is around 350 acres of land. We are the first establishment for dedicated for electrochemistry, and you can see here the institute name is I'm sorry, I think this is disturbing me. Okay, so this is the entrance of our institute, and I put this image for some reason. This entrance was the entrance where Jawaharlal Nehru, Sir Vapalli Radhakrishna, and Sir C.V. Raman, Dr. APJ Abdul Kalam, everyone walked through this entrance, walked through these steps, and we are also walking through this steps. So that is the pride I would like to take at this moment. And you can also see a couple of statues at the entrance. So on one side, you are seeing Michael Faraday, the father of electrochemistry in general. And on the other side, you can see Sir C.V. Raman, whose contribution to molecular chemistry and, of course, in general, in chemistry is it cannot be denied by anyone. So his contribution is enormous through his discovery of Raman effect. And at the center, you are seeing a portrait of Mahatma Gandhi ji. So this is all about. I just wanted to highlight today to you. Sorry. Yeah, moving it. So the institute, as I said, it is the dedicated establishment for electrochemistry, and we work various facets of electrochemistry. We put in a major 6 baskets, starting from corrosion and material protection, power sources, including batteries and superfast fuel cells and so on, electroorganics and materials electrochemistry. We develop a lot of catalysts and for various electrochemical industrial reactions, and electroplating and electrometallurgy, very well known for its applications in automobiles, in plants, and so on. And process engineering, we work on hydrogen production in this division. And finally, the highlighted one, the electronics and electrocatalysis, where we work mainly on the fundamentals of electrochemistry. And I'm from this division, electronics and electrocatalysis. And this is my laboratories. This is my group. I'm from Analytical Microsystem Laboratory. I lead this lab. And here we have our team. And as I said, we are working on spectroelectrochemistry and microfabrication of sensors. So today, as the topic describes you, I will talk something about the new type of transistors. I'm sure this is being an engineering institution, you might have come across transistors, and you know very well the basic characteristics of transistors and what is it and how it is working and so on. But today I'll be talking about something different, which I don't know how many of you are aware of it. It is called electrochemical transistors. Generally, transistors are known as electronic devices, but today I will be talking about electrochemical transistors and its applications in sensors. I will talk about what is it and why it should be used, the advantages, and finally, how we are deploying it for sensors. To start with transistors, the fundamental of what we are doing, it starts all the way exactly 100 years back. In 1925, Professor Edgar has proposed a theory saying that there is something called a trans-resistive property when we have a semiconductor. So at that time, people were thinking that only conductors have the advantages, not the semiconductors were not explored much. So Edgar said it has its own switching applications, but he couldn't demonstrate practically because of the non-availability of pure semiconductors at the time. Around 22 years later, 3 scientists from Bell Laboratory, John Bardeen and Breton and Shockley, and all the 3 scientists started exploring his theory and tried to visualize it in experimental way. And they have realized and they have demonstrated that a semiconductor can be used to make switches. Okay? And the switch is called transistors. And you know, transistor is nothing but a trans resistor. It's simply a resistor, but you can modulate its resistance by applying a third potential or third electrode, using a third electrode called gate or base or whatever it may be, depending on the type of transistors. And what you are seeing here is the simplest model. I don't know whether my cursor is visible there. Is it visible? Yes. Okay. So this is the basic model they have developed, and you can see here there is a gold foil, and which will work as a base, and you have a semiconductor, and the two sides of this triangle is your source and emitter. And these are different type of transistors. I really do not want to get into these details, but I wanted to get your attention on this MOSFET, metal oxide semiconductor FET. So in this latest, I mean, at that time, it was in 1965 or so, the MOSFET was introduced, and you can see here the metal is nothing but your gate, oxide is your dielectric layer, and semiconductor is your base as well as your channel region. The channel is a temporary one, and it is induced by your gate potential. And depending on the polarity of your gate, your channel thickness will either increase or decrease, and that is what we call as a transistor. And here, I will just explain you one important concept, but you will understand why it is so important in the next few slides. The dielectric constant. When you are using a dielectric, gate dielectric here, definitely this dielectric will have its own dielectric constant. If you take air or vacuum, the dielectric constant is 1. And the very widely used dielectric in semiconductors is the SiO2. And it has the dielectric constant of 3.9. And it really depends on its structure. So it varies. And on the other hand, if you see silicon nitride, there is one more dielectric used in transistors, but not very widely as silicon oxide. If you see that, it has 7.5. But if you see water, it is 80, almost 10 times of silicon nitride. Okay, just understand that dielectric constant means how easy it is to polarize. How easy it is to polarize. So the higher the dielectric constant, easier it is to polarize. Lower the dielectric constant, it's difficult to polarize. So let us understand how it helps in transistors in subsequent slides. After the development of transistors, maybe after 30 years, in 1986, Professor Ando and his group has proposed a new type of transistor, which is very similar to our MOSFET, but in that MOSFET, the semiconductor part was simply replaced with some organic material or organic semiconductor made up of polythiophene. And they call it as organic FET or OFET. This is the starting point of electrochemical FET. The reason is, unless otherwise you have these type of organic channel materials, it is not possible to realize your electrochemical FET. And we can see the channel and if you see the channel charge or channel conductivity is modulated by the gate potential, where inducing a layer of charge. Okay, that is the basic principle in MOSFET. And the signal, whatever you are giving to gate, will actually transform into the channel current. If you see, if you know what the structure of your semiconductor, MOSFET structure, you actually give the potential to gate, but that will be transformed into the channel conductance. Okay? So here is some equations. I really don't want to spam you with a lot of information about these equations, but simple thing, I wanted to get your attention on 3 things here. One is W, L, and C. W is, if you take any transistor, there will be, in MOSFET, there will be 3 leads. One is gate, another one is source and drain. The channel will be between source and drain. So that is what you are seeing here. You have a source, you have a drain, and you have a gate. And the channel is between source and drain. Okay, you give a potential between source and drain to drive the charges here. On the other hand, you give a potential to gate to modulate the charge. Okay, so this is the basic principle of MOSFET or OFET, both are same. Okay, in this case, you are you know that the drain current, whatever the current is flowing between the source and drain, is proportional to the width of your channel. Okay, width width of your channel, and inversely proportional to the length of channel. Length of channel means it's a distance between your source and drain. Width is nothing but your width of your source electrode and drain electrode. Both will be equally long. So on the other hand, it is also directly proportional to the capacitance. The capacitance. From where this capacitance come now? If you see here, once again, let's go back. You see here, this is a semiconductor, and when you apply potential, there will be a blanket of charge accumulated on the surface. So you can very well think that as a metal sheet. Okay, accumulation of charge which is free to move is nothing but a metal sheet. Okay. On the other hand, you have a gate which is already a metal. If you sandwich an insulator between two metal, then it's a capacitor. It's a simple architecture. So this capacitance matters in when you calculate the drain current. Okay. Now, if you take this capacitance, it has its own equation. If you see, this capacitance is proportional to the area, inversely proportional to D. D is nothing but L here. D and L are same. Okay. And apart from that, it is also proportional to the dielectric constant. Okay. Now, the length L, width W, and area A, all these three will be precisely controlled by microfabrication. So we have a microfabrication facility. We make very micron-sized transistors, so that all these three factors are already taken care. But one thing which is not taken, which is not accountable by this microfabrication, is the dielectric constant. Okay, capacitance is proportional to dielectric constant, and ID, the drain current, is proportional to capacitance. So obviously, drain current is proportional to dielectric constant. So now let us try to understand what we can do apart from this W and L and A. Okay. Already we have seen these numbers. For SiO2, the dielectric constant is 3.9, and Si3 and 4 silicon nitride, it is 7.4. I already said that higher the dielectric constant, easier it is to polarize. Now let us look into this graph. Here you are seeing the dielectric constant of a salt solution. Simply just take a sodium chloride solution. In sodium chloride solution, just see this y-axis, the number is somewhere in 80s and 90s. So it is almost one order higher than what you get with the silicon nitride, or at least 20 times higher than your silicon oxide. What does it mean? Means that the potential you need to polarize is very less. That is why if you see generally our electronics, it typically works at 5 volt. The 5 volt is not necessary for your semiconductor channel. It is necessary for your gate dielectric to polarize. So that is why it is working at 5 volt, though silicon's band gap is only 1.1 electron volt. Okay. And the switching speed is also very good. It is 0.3 milliseconds. Of course, it is you cannot compare it with electronic transistors with switching speed, but still for other purposes, it is good. Okay. So how can we use this electrolyte? Where should we use? Obviously, in the place of dielectric, like silicon oxide. And it is not going to be that easy, and it is not going to have electronic applications, because you cannot put any liquid into your IC. So we use it for sensing applications. If you see here, let me just draw a parallel between the MOSFET. Already most of you know what is MOSFET. I'll try to draw a parallel with the EGO FET. In MOSFET, you have a source and drain. Obviously, here also you will have source and drain, and you will have a gate. Obviously, you will have a gate. And here in MOSFET, you have a dielectric layer made up of either silicon oxide or silicon nitride. But here it will be a salt solution, or say some gel polymer electrolyte, or so on. Okay, it is not going to be a conventional dielectric. And when you apply potential, what happens in your MOSFET? To gate, if you apply a negative potential, it will polarize the dielectric in such a way that the gate interface will have accumulation of positive charge because of the electrostatic attraction, and the other surface of the dielectric will have induced negative charge because of the repulsion. And this accumulation of negative charge on the other side will accumulate positive charge in the channel. So your channel will be now will have more holes. So it will work like a highly doped or heavily doped p-type semiconductor. Okay. Similarly, here also, when you apply a negative charge to your gate, it will attract the positive charge. In a solution, particularly in a sodium chloride solution, sodium will be Na plus and chlorine will be Cl minus. So sodium ions will be accumulating at the gate electrolyte interface, and the chlorine will be accumulated at the channel electrolyte interface. So you have now two interfaces. Obviously, you have two capacitors. If charges are separated with a non-zero distance, then it is a capacitor. So you have a channel electrolyte capacitor and electrolyte gate capacitor. Okay, so the same thing goes here also. This is the analogy between the electrolyte gated OFET and MOSFET. And now, how can we use it for some sensors? For instance, now we know we have two capacitors, okay, at the channel interface and the gate interface. In case, just imagine in case I have already put some biological adsorbent, okay, which will selectively adsorb some biological molecule on the surface of gate. What will happen when I put the specific molecule? Initially, it will have its own effective gate potential. When the specific molecule comes, the gate potential, the adsorbent will absorb the molecule, and the gate potential will change. And when the gate potential changes, obviously it will the degree of modulation on your channel will change. Then obviously the drain current will change. So this is the basic principle, and this principle can be used for so many different biosensors that I will just explain to you. Here, just for an example, I have given one simple sensor where the DNA hybridization can be detected. How? You just functionalize your gate or functionalize your channel with one single stranded DNA. And when you put the mixer of single stranded DNAs, when these two DNA sequences are matches, okay, if you have some DNA which matches the sequence well with the functionalized DNA, then it will hybridize. When it is hybridizing, then obviously the surface is populated more mono single stranded DNAs. Obviously, the electric double layer or the capacitor will change. Then obviously you will get a different current in your source drain channel. Okay. So let us just get one example here. It is the EG based immunosensor. Already I have explained. Here they have taken some antibody, okay, and it's in human immunoglobulin antibody they have taken, and that is specific to particular antigen. Okay, so they take anti-IgG and IgG. So these are actually coupled. You can put either one on the surface to get another one. The reason is these two are biologically conjugating. Okay, these two will attract each other. So in case if I have one molecule, either AGG or anti-AGG, I can put it on the gate or on the channel. And whenever I give some sample which has the complementary one, then obviously it will be absorbed and the biocomplexation happens on the surface. That will lead to the alteration of electric double layer. That alteration will be converted into the electrostatic, surface potential of your gate. And if the gate potential changes, obviously the channel will change. Here, one important point in this electrolyte gated OFET is the trans conductance. I'll just explain that in a coming slide, but now you just understand when you change potential to any resistor. Let us take a simple resistor. It will it is a ohmic device. It will follow Ohm's law, V equal to IR. Now, if I change voltage for a constant resistance, my current will change. Okay, but in a transistor, you have two voltages. One is the source drain voltage, another one is source gate voltage, VGS. Okay, gate source voltage. Now, what you are doing is when you change the source drain voltage, obviously the source drain current will change. But when you change source gate voltage also, your source drain current will change. And this change or this change in conductivity or conductance is called transconductance, because here it is not a direct ohmic method. It is trans method. Okay, the transfer method. So that is why it's called transconductance. Okay. And the electrolyte gated OFET has simple polarization. Okay, we have seen MOSFET where the charge polarization is simple, and we have also seen EG OFET. Here also the charge polarization is simple polarization, but here we have a free ions. So that is why we said we will have a higher transconductance. But on the other hand, organic electrochemical transistors, OECTs, okay, these are somewhat similar to EG OFET. This is also having a OFET structure. This is also having electrolyte. This also has a gate which is connected by other electrolyte. But the only difference between the OECT and EG OFET is the electrochemical reaction. In OECT, there will be an electrochemical reaction. There will be a charge transfer between either gate and electrolyte species or electrolyte species and channel. So this will be there. And in case if you take this polymer, generally it's a benchmark polymer. Most of you may know it's called PE.PSS. Okay. This is a stabilized polymer in water. It's a conducting polymer, P-type polymer. And if you just add some M plus is kind of, let us just take it as proton, okay, H plus, okay. M is a generalized word. So let us take it is a H plus, and if you put one electron together, it will produce P dot 0. The P dot plus is conductive, okay, because it's a P-type conductor, so it needs a net positive charge. But when it is neutralized, it is not so conductive. Okay, so that is why you will have a lesser conductivity here. But when you once again oxidize it back, take the electron out, and if you make the P.PSS, then the conductivity will be higher. So this this electrochemical process can be utilized for sensing purpose. What are the things we can do? You can put you can make a OECT with a P.PSS channel, which is between which is connecting the source and the drain. On the other hand, you have a gate, and on the gate you can put some biological molecule for biofunctionalization. And if there is any electrochemical reaction or chemical reaction, biological reaction, anything happens on gate, if it is producing some proton, just imagine if it is producing some proton, then that proton will come to the channel and it will neutralize the channel to reduce its conductivity. And that can be taken as a signal. On the other hand, you can also put some biological bioreceptors on the channel as well. Okay, so those examples we can see in a subsequent slides. Let us just take this simple example. Here, you just take an OECT. Okay, you are seeing here 3 electrodes totally. Just assume that it is source and drain, and you have also separate gate electrode here. Okay. Now this gate electrode is functionalized with some antibody. Okay, some antibody. Don't worry about which antibody it is. Some antibody. And on the other hand, you have taken one more gate electrode and simply put some horseradish peroxide. Okay. And then BS, it's bovine serum albumin. Don't worry about it. Is just to protect your unfunctionalized surface to act on your analyte. So one electrode is functionalized with the horseradish peroxide, and another one is functionalized with the antibody. So that much you just understand. Now, if you the horseradish peroxide has some property. Whenever you put some peroxide, like hydrogen peroxide, H2O2, it will oxidize it into, it will reduce it into H2 water. Okay. Now, you just take this electrode and see here the figure 1, okay, the top figure. If you see here, whenever they put a different concentration of H2O2 at this point, okay, they put the same amount of H2O2, but a different degree of horseradish peroxide functionalization. You could clearly see the changes in current, okay. IDS is changing. What does it mean? Though the concentration of H2O2 is same, if you change the horseradish peroxide concentration on the surface, you can get different current. Okay, let us try to understand how it can be used for sensing purpose. Now, I said the second electrode is functionalized with some antibody, and this antibody will have a very selective absorption towards some protein or some cells, okay, some cancer cells. All the cells will have its own protein. Cancer cells also will have its own protein, but this particular protein will be specific for this cell. So if you find out that the protein is there in the cell, you can find out that this is a cancerous cell. If it is not, it is a normal cell. So that is the simple philosophy we are going to use to distinguish between a normal and cancerous cell. Okay. Now you just take this electrode. Okay. In one electrode, you just simply put some horseradish peroxide, which is functionalized, which is tagged with, I'm sorry, you just put some protein, which is specific to this antibody. So when you put that protein, definitely it will absorb. Okay. And if you have a probe, it's called nanoprobe, where the horseradish peroxide is attached to the particular same antibody, but we call it as a counter antibody. Okay. If you have this nanoprobe and already you have a protein, and that protein is attached to the antibody on one side and other sides are free. Now, if you put the nanoprobe will go and attach on the top or side somewhere. Okay. And this is called a sandwich assay. We call it as a sandwich assay because it, two antibodies are sandwiching the protein. Okay. So now you can see here, you are introducing the same amount of H2O2, and now you are changing only the protein HER2. HER2 is a protein which is in the cancer cell. Okay. So it means that with the change in amount of protein, you can actually tell how much the protein is there. Okay. Or with the change in amount of protein, you can get different current. Now, let me just ask you, is it not possible to count the cell using this? Because just assume that one cancer cell has 1 unit of this protein. If I have 10 cancer cells, obviously I will have 10 unit of protein. Okay, so now let us take one more for the same electrode. Now I'm not going to put the protein, but I'm going to put the cancer cell which has this protein on the cell wall. Now what will happen? Obviously the cancer cell will be attached on the antibody. Okay, and the cell wall will have obviously more number of protein. Now if I put the nanoprobe, this nanoprobe will go and sit on some places of the cell wall, right? So now this current change is proportional to the number of cells. You can clearly see here. If I have 10 cells, you have this much current, and if it is 100, you have a different current. If it is 1000, you have different current. So this is how we can precisely identify whether a cell is a normal cell or cancerous cell. And even if it is, it is not only identifying, you can even quantify it. So this is one good example. And the second example is pretty much same. Okay. Here they have demonstrated the detection of a single-stranded DNA. Already I told you a couple of slides back, if you functionalize the gate electrode with a single-strand DNA with particular sequence, when you introduce this different sequence, definitely it is not going to hybridize. It is not going to make that double helical structure. But if you introduce the same sequence, it will make the double helical structure. So with this, you can find out the presence of a particular sequence of DNA in your sample. If you know that a particular sequence of DNA is there in your sample, then obviously you can know you have a certain protein. You have you can just assign that to certain protein or certain cell and so on. Okay. And this is what we have done. From now, I will just present what we have done so far. This is a small piece of work that I wanted to highlight today. So this is our first attempt on OECD, and here we have used some N-type polymer. Already I said in OECTs as a channel, the demonstrated ones are P-type polymer, which is commercialized already. But here we have an N-type polymer. The very big advantage of N-type polymer is whenever there is something is some molecule is getting oxidized, because that is more probable. Most of the molecules get oxidized. In neutral case, it will not be charged, but mostly they will get oxidized. When they get oxidized, they will receive electrons. Okay, and your polymer should be ready to handle those electrons. So that is why the N-type polymer is very special. And we use this polymer in the channel. You can see here, this is actually a 10 micron line, and the channel width here is 1 micron. And this is your source, drain, and you have a gate here. And you can see if this is 10 micron, this overall electrode size would be hardly 30 microns, okay, 30 or 40 microns. So we made this device by microfabrication, and we made this device by microfabrication, and we have tested it for glucose sensing. You can see here it is giving a gradual response to the glucose concentration. Okay, but this is not the very exciting thing to publish this paper in Nature. We have done something extra, where the same device has been demonstrated as a enzymatic biofluorescence. The reason is, for glucose sensing, on the gate we put the glucose oxidase enzyme. Okay, and we have counter electrodes also here. Why don't we use these two electrodes as a fuel cell electrode? We have two electrodes separated by some electrolyte, nothing but a fuel cell. Okay, and since we have enzyme here, it's an enzymatic fuel cell. So we demonstrated that using this same configuration without doing anything. You can see here, this is source, drain, gate, and on the other side, you also have, you can call it as another source and drain. You can take one pair for sensing purpose, another pair for your energy generation purpose. What is the advantage of? You can generate electricity that is required for this sensor within the sensor itself. So in case if in the future, if you wanted to put some sensor into your body, calling we famously known as the implantable sensors. If you wanted to implant your sensor, then you need to supply some electricity. Without the electricity, how the sensor inside the body is going to function? So obviously you need electricity, and if that electricity is produced inside the body, then obviously you will have a lot of advantages. And that is what we have demonstrated, and we have published this paper in Nature Materials. And this one is the recent development. We have developed a cylindrical diffusion OECT. Okay, generally in electrochemistry, if you take a very big electrodes, the diffusion will have its own impact. Okay, there are two things governing electrochemistry. One is the kinetic limitation, another one is diffusion limitation. Generally, the kinetic limitations are handled by the catalyst. That is why you need a catalyst. So you design your catalyst in such a way that it will give or extract electrons easily, so that you will reduce the potential. Okay, you will reduce the potential. That is one side. But on the other side, the diffusion limitations. Diffusion limitations cannot be handled simply by changing your catalyst. You need to change the geometry. Okay, a planar diffusion will always look something like this, so that the approach of the species is one-dimensional. It will always go from the top to bottom, or left to right, or bottom to whatever it may be. So it will be a one-dimensional approach. So the competition between for a unit area, the number of charges approaching the area will be very less. Okay. On the other hand, if you take a spherical diffusion, for this area, you are getting approach from all the hemispherical directions, all the 360 degrees and 180 degree. Okay. So all the hemispherical area is giving you the charges. It is like you just imagine you have a very big mob coming from one side to other side, and you have a sequence of shops, sequence of counters. So the number of people approaching the counter will be very less. So in a simple manner, if you want to, if 1,000 people are coming forward and you have 100 counters, each counter will handle 10 people. And 1,000 people are coming, you have only 10 counters. So each counter has to handle 100 people. Okay, so that is how here, if you make a hemispherical diffusion, you can increase the number of species approaching the electron. But this hemispherical concept cannot be used in transistors, because on a single electrode it is possible. But in transistors, you have a source and drain, and your channel will be attached between these two electrodes. So there is no use of this spherical diffusion concept in our case. But you can use it for you can use cylindrical diffusion. You can take a cylindrical wire and put it on the two so electrode source and drain. Now, if you put an electrolyte, all the 360 degree, your species will approach the electrode. Now, we just took a very simple approach here. We took cotton fiber. The cotton fiber is typically of 10 to 15 micron of its size. And we coated the conducting polymer PSS. And you can see here the inner side, the grayish color or bluish color is your cotton, and on the other side of outer side you have a PSS polymer. And overall, the overall dimension is roughly 10 microns. Okay, and we attached the fiber on OECT as a channel, and then we have demonstrated a sensor. And here we have claimed that it has it may have a cylindrical diffusion. But how to prove it? We took help from the impedance spectroscopy, because the impedance, if you see, this is the charge transfer, the kinetic region, but the lower frequency or higher impedance region is your diffusion regions. And this region, the impedance depends purely on the type of diffusion, whether it is a planar diffusion or a spherical diffusion or cylindrical diffusion. For a cylindrical diffusion, it will show something like a very less slopy behavior. You can see here, this is from the literature. So we have also observed for our P.PSS with coated on cotton microfiber, we also got a similar profile. So we, with the impedance spectroscopy, we confirmed that our electrode has a good cylindrical diffusion. And to confirm it, we have also tested some other electrodes. Say, if you take a simple glassy carbon with P.PSS, you can see it is pretty much parallel to your imaginary axis. Something parallel to imaginary axis, it means that it is a double layer property. Okay, and here also, if you take another one, polyimide strip, once again it is a strip like a planar structure. So you have a diffusion region pretty much close to your imaginary axis. And if you take a carbon microfilament with P.PSS, which is well-known conducting filament, you are seeing once again the saturation kind of profile. So this tells us whenever you use any cylindrical electrode, you are or microfiber electrode, you are actually getting the cylindrical diffusion. Okay, so now we proved that we can achieve the cylindrical diffusion, and we wanted to use it in our device. Okay. Let me just, I think I was supposed to put this image over there, but I just moved it here. So this is how we have created our device. You are seeing a source, drain, and in between we have a P.PSS coated cotton filament. And then here you have a gate electrode, and that gate electrode is functionalized. That what I will come later. Okay, so this is what we have done so far. Okay. So now we have created an OUCT with this microfiber channel, cylindrical channel, and we tested its IV characteristics. Generally, you know, the IV characteristics for a ohmic device will be a straight line, something like this. Okay, and if you see your O fit or fit, you will see a linear region and then a saturation region called pinch-off region. But in this case, if you see, the profile itself is something crazy. It is not a linear profile. And this is not the first time we observe. It is already observed and well known for OUCTs, not for other transistors. For OUCTs, it is very well known. And the behavior was completely studied by Bernard and Mulliaris. And they have introduced an equation with their name, Bernard-Mulliaris equation. And you can see here, whenever the potential, whenever the source drain potential is less than the gate potential, you will have a non-linear profile. Okay, but if it is if it is greater than gate voltage, you will have a linear profile. Okay, so that is why here it is non-linear. But when the potential crosses, for example, let us take the VG is equal to 0 volt, the red line. Here it is non-linear, but after 0, you can see a very nice linearity here. Okay, so but if you take 0.6 volt VG, it is non-linear here. It is going on non-linear here. Okay, so this is what we have seen in the literature, and we also achieved it. So from this we can understand that our transistor, our OUCT is working perfectly. Okay. On the other hand, the transfer characteristics tells you how much your electrode can get the conductivity in your system. For instance, in case if your gate has no effect on your channel conductance, if there is no transconductance at all, then you will have a very parallel straight line. Okay, very parallel straight line parallel to your x-axis. But what you are seeing is there is some change. Okay, where we see the top curve, there is a clear change. It means that the potential applied to gate is actually modulating the current in the channel. So that is what we have achieved. So already we have seen here, and the same concept in a different plot has been concluded here. Okay, with the transfer characteristics, it is once again reaffirmed. And then we have fabricated the OUCT successfully. Now we wanted to test its capability to use for biosensor. Still, it is not a biosensor. We are just trying to test its capabilities for different scenarios. For instance, in case if I change the pH, what happens when I mean less than 6 pH, it is stable, but when you increase the pH to higher one, say 7 or so, the conductivity drops. Okay, but remember our physiological pH is 7.35, so 7.34. So we should be working somewhere in this region. On the other hand, if you see the electrolyte concentration, that also can affect. The reason is your body may have different concentration of electrolyte. Particularly, we have used this device for sweat glucose sensing applications. So obviously, sweat will have different concentration of salt depending on our body's hydration and the outside environment. So we have tested the transistor with a different ionic concentration, so ionic strength. So obviously the ionic strength changes the conductivity. So in when we use this transistor, first we have to analyze the ionic conductivity. Then we have to find out the glucose concentration. So it has to be offset. So that's what we would like to tell you. On the other hand, this is very important observation. The transistor works really consistent with different amount of electrolyte or different amount of sample. Starting from 20 microliter all the way up to 160 microliter, there is no change in IV characteristics. It means that even with 20 microliter, you can get the consistent result. That is that you can get with 100 or 160 microliters. On the other hand, we have also checked the effect of additive, because when we code P.PSS, we put different additives. So we found that the DMF dispersion gives a better conductivity. So we generally use it during coating purpose. All right, so we have fabricated the sensor. We have completely tested the sensor at different conditions as well. Now the sensor showed a very good capability to use it as a, I mean, the OECT has shown a very good capability to use it as a sensor. Okay. Now, if it has to be used for glucose sensing, it can be used for any other sensor. Okay. Now, so far, what we have seen is the platform, the OECT platform. Now it can be either used as a glucose sensor or immunosensor, or even for living cell. You can use it. So in this work, we have demonstrated it as a glucose sensor simply. Okay. So in case if you wanted to selectively sense glucose, obviously you need something that responds to glucose only, nothing but your glucose oxidase enzyme. So we have bioconjugated our gate electrode using glucose oxidase, where it is a several step process, but simply we have just given the procedure. It's called, so it's famously called the EDC NHS procedure. So at the end, you will get a glucose oxidase immobilized on the gate electrode. Okay. Now this is your final sensor device. You have the conducting polymer coated cotton fiber as a channel between source and drain, and your gate electrode is functionalized with glucose oxidase. Now, in case if you put a molecule of glucose, if you add an electrolyte completely connecting the gate electrode and the channel, and if you put one glucose molecule, what will happen? So that is what we have to understand. The glucose will be oxidized into gluconolactone by FAD, okay, flaminin adenine dinucleotide, okay, dinucleotide. So this FAD will oxidize your glucose into gluconolactone, and in this process, this FAD will be reduced into FADH2. It will just acquire 2 hydrogen. Now, this is actually a spontaneous chemical reaction. It is not an electrochemical reaction. It's a chemical reaction. Now this gluconolactone will react with water to produce gluconic acid. On the other hand, this FAD H2, the reduced form of FAD, will react with oxygen, dissolved oxygen in the electrolyte. It will form what H2O2, and it will regenerate the FAD back. And this FAD once again will go to oxidize one more glucose molecule. Okay. Now everything is fine. Finally, you are getting one H2O2 molecule. This H2O2 molecule is going to make you sensing the glucose because it is proportional to the glucose concentration. When you add H2O2, the gold electrode surface potential will change. And we have a proof for that in the subsequent slide. I'll show you. So the concentration of H2O2 will change the surface potential of this gate electrode. If the surface potential is changed, obviously the degree of modulation will change and the channel conductivity will change. And this is the basic sensing mechanism. And with this mechanism, we have seen the response of this device to glucose. And here with the different concentration of glucose, you can see the IV plot is going down. It is actually the conductivity is going down. Obviously, I said already, when you produce more amount of hydrogen, the hydrogen will go and de-dope your P.PSS, and the conductivity will go down. And this mode is called a depletion mode. Okay. And the same changes are observed in the transfer characteristics also. And the extracted values are given here. You can clearly see when you increase the concentration, you are actually seeing the decrease in ID, the drain current. In this device, we repeatedly seen that this slope, actually it was supposed to be a clear step, but we have seen a slope. So that's why we have used this IV characteristics, which is more stable for subsequent analysis. And the extracted values are giving the normalized current ratio. This normalized current ratio tells you how much your sensor is responding per unit amount of glucose concentration. Okay. And you can see here, this is the responsibility curve. Your y-axis is microampere. The microampere current change per 1 milligram per deciliter change in concentration. Okay. And you can see as good as almost 1.8 or 1.9. What's happening? Oh, I'm seeing some lines. I think someone is writing on the screen. Oh my God. I'm seeing a lot of lines. Someone is writing on my screen, I guess. Could you please just delete it? Or... Okay. I'm also seeing one red line, which I couldn't delete. Could someone please delete it? Okay. So the device gives me almost 1.8 microampere. Microampere is a very good current per milligram per deciliter, which can be easily handled by even a very less sophisticated electronics, and that we will demonstrate in this next slide. Okay. And the final one is the interference. When I have a sensor for glucose, I should sense only glucose. The other constituents should not get sensed, or the sensor should not respond to that. So the main constituents are uric acid, dopamine, and ascorbic acid. All of them are tested as an interferent, and they have no significant response in this device. And with this confident, we have also developed our own electronics, because we got microampere current, which is very easy to handle with normal electronics. So we made our electronics as well as our algorithm, and we got this response. You can see here, when the glucose concentration increases, the response increases, the net current response increases. From this NCR curve, what I wanted to highlight here is the response, the change in response when you change the concentration is very steeper at lower concentration. and it is not, it is still changing, but the slope is less here. The slope is very high here. This tells us that the sensor is working very precise, or very, the responsivity is much better at a lower concentration. So that is why we did not use it for blood level of glucose, because the blood level of glucose will change typically from 50 milligram per deciliter to all the way to 500 or even higher. Anything less than 70 is called hypoglycemic, and more than 120 is called hyperglycemic. So now, if you take the level in sweat, it will be typically 30 to 50 maximum. So if you see that range, 50 is somewhere here. So in this range, we have a very good responsivity. So that's why we use this device for sweat glucose. And you can see it's a very small device. And these two dots are actually the channel, and this is your gate. And whatever the fingerprint you are seeing here for your response, and it is a flexible device as well. You can just bend it or even twist it, and you can wear it on the hand to get the glucose concentration in our sweat. And we made an electronics, and with this electronics we have just derived the NCR value. From this NCR value, we can get the glucose concentration if you give me any unknown sample. Okay. And this is another work. I think I have at least 15 minutes more. So there's another work here. We have developed a self-biased replaceable gate based OACT for a glucose sensor. Once again, if you see the first work which is published in Nature, we highlighted the importance of self-biased or self-powered. The reason is for any sensor, you have to give some electrical energy. If you have to give electrical energy, then obviously the circuit will be complex. And already our transistor-based sensors will have 3 leads: source, drain, and gate. So obviously all the 3 leads should be electrically connected. So that increases the circuitry complexities. So how can we reduce that? How can we reduce the power supply to gate electrode? And how can we reduce the circuit complexity as well? So that is what the main motto of this work. If you see here, we have used a configuration called extended gate configuration. In this configuration, it has several advantages. I just highlight only 3 here. The extended gate allows you to functionalize the gate electrode easily, because it's like a strip, and you can simply put it in a bath of your sample, bath of your chemicals, and it will be functionalized. It's very easy. In case if you have a micro fabricated sensor, the one like what I have shown before, it is the electrodes are very small, and you have to precisely functionalize it. In case if it is not precisely functional, if it is just going to other electrodes, then obviously it is not going to be useful, and it is wasted. But here it is not like that. You have a strip, and just dip the strip, it will be functionalized. Very easy to functionalize it, bioconjugate it. And secondly, the self-biasing design will reduce the power requirement, and it also will reduce the circuit complexity. And we have also, in this work, we have also demonstrated that the gate can be replaced. You can keep the source, drain, channel, and the electrolyte, dielectric. Everything can be constant. Only the gate electrode can be just used for one sensing application. Then throw it and then take one more. That's like pretty much like our current day glucose sensor, where you get a strip for 10 rupees and insert in the device and put your blood. Then it will sense the glucose, and after sensing, you will just throw that strip and put on more for the next analysis. So that is what we have demonstrated here in our device. So we have this is the typical fabrication. So we have just used SiO2 silicon with the SiO2 layer, 300 nanometer SiO2 layer. as a substrate. On that, we have first deposited source and drain gold pads using E-beam evaporation. Then on that, we have coated P.PSS as a channel using Dr. Blade method. Then the surface is masked because we are going to insert our electrode and gate electrode, and just it will be removed and inserted several times. So at no point the gate electrode should directly touch either the source or drain. So that's why we just masked that surface with a PMMA, polymethyl methacrylate. Then we deposited the gel polymer electrolyte made up of PVA and NaCl as the mobile phase. So this is the complete module. This is the complete source drain electrolyte dielectric module. Okay. On the other hand, we need one more thing is the gate electrode. So the gate electrode is prepared by polyimide sheet. On that, we coated gold using E-beam evaporation. Then we using EDC NHS mechanism, we bio-conjugated the electrode with glucose oxidase. Then this electrode is ready for sensing purpose now. Now we have to integrate this gate electrode with the source drain channel electrolyte module. So if you integrate it, you will get the device like this. This is the digital real device photograph. And so it's actually zoomed. The overall device dimension is not so big. It is magnified one. And now this device, in here, two things are very critical now. Okay, one is how efficient your gate can work. That means there are some chemical reaction going to happen on the gate surface. If that chemical reaction can be converted into some electrochemical potential or electrical potential, then this electrode does not need any external voltage. Whatever the chemical potential generated on the surface will itself will suffice to modulate the conductivity in the channel. This is one thing. So we have to test the gate electrode separately, how efficient it is. On the other hand, now I have created some potential. Let us assume that we have created some potential using the chemical reaction. This potential should be transferred into the polarization effect on the channel. So there is a transconductance or transfer characteristics. So that is also important. So if my electrolyte should have a better transfer characteristics, I mean, my device should have a better transfer characteristics, my electrolyte should have a particular property. It should have a very high conductivity. That is very important. There should be a high amount of mobile phase. There should be no electrolyte depletion at any point, at any case. So I can put a lot of NaCl salt, but the problem is when you put too much of NaCl and too much of water, the electrolyte will not be a gel polymer, it will be a liquid electrolyte. So I need the gel shape, the structural integrity should be there, but still I need a better electrolyte conductivity, ionic conductivity. Okay, so this is what we have optimized in this case. We have we have made a NaCl PVA gel polymer electrolyte with a different NaCl loading. And you can see when I change the NaCl concentration, the ionic conductivity is gradually changed, but it is getting into some saturation. Okay. And the transconductance, when I use this electrolyte into the OSCT as an electrolyte, okay, as a dielectric, then I will get the transconductance. The transconductance is also gradually increasing, going all the way to 6 to 8%. Okay. And if I calculate if I want to calculate the activation energy, I need to do a temperature dependent study, and we have done it, and we fit those data with Arrhenius plot. From this fit, we extracted the activation energy, and this activation energy is somewhat almost similar, though it looks it is changing from 1.46, 1.59, and 1.88. But for this change in weight percentage, this change is pretty minimal. So we can take anything in between. So we have taken generally 3 weight percent NaCl, PVA, GPE for subsequent studies. And now we have optimized the electrolyte or the dielectric gel polymer. On the other hand, we also have to optimize the channel and gate. So on the channel, already I told you in the previous study, we have used DMF as a additive, and here also we have used DMF. There we have optimized with the different solvents. We studied with different solvent, but here we have directly we used DMF with the previous knowledge. And you can see here when I change the P.PSS weight percentage, we got gradually increasing conductivity. For instance, at 2 weight percent, we got the highest conductivity. But beyond this, it is not possible because we have to add a DMF, and the standard concentration for P.PSS is 5% so in water. So we have to remaining is DMF, the minimum DMF requirement. So with 2 8%, we got a higher conductivity. So we used it as a channel coating material. Okay. The conductance also we have calculated. It is 0.12 millisiemens for 1 weight%, but for 2 weight%, it is 0.25 millisiemens. And we already in 3 climbs, I said in 1 climb it is a replaceable gate. That means you will have the complete source drain channel and electrolyte as a module. Only you can use the gate as a sensor, and after using, you can throw it and you can put one more sensor. In this study, we have checked 2 different things. One is, can we use the same module for different gates? And you can see here we have used for the 5 different gates, but with the same device, same source drain module, but 5 different gates. It is completely reusable. That is one thing we have demonstrated here. Secondly, with the different gate area, we got almost the same drain current. That means the drain current is not a function of gate area. It is a function of only the chemistry, the surface chemistry happening over there. You can see on air, you have almost 1200 microampere, but on ethanol solution, inside ethanol solution, it is around 850. Inside mercaptobenzoic acid, which has a very strong affinity towards gold electrode, we have around 700 microampere. So it completely depends only on the chemistry on the electrolyte electrolyte gate interface. So these are the 3 things we have proved with this study. And now our device is ready. You can see the IV characteristics. Once again, it is not a linear one. Already we have seen the Bernard-Mulliaris equation. It is not it's a non-linear equation, and it is satisfying that equation. And you can also see a finite slope here. So the transfer characteristics is also good. It is not. I mean, the gate is actually modulating the channel conductors. But when you change the gate potential to positive, for achieving a high very importantly, we have calculated the pinch off voltage, and it is gradually increasing with increasing gate voltage. So all these things are the typical characteristics of your OECTs. So the device works perfectly as a OECT. Now we can use it for biosensing purpose. And we have tested the device for a different glucose concentration. Okay. Starting from 1 milligram per deciliter to 500 milligram per deciliter, and you can clearly see there is a gradual change in the slope. Okay, if you extract the value from this IV characteristics, you got a slope something like this. Here you can see the difference. In the previous study, we have seen the sharp increase in response at lower concentration. Here also we are seeing the same trend, but the one big difference here is the response at the higher concentration. The higher concentration slope is comparably good when compared to the previous study. There we used a very small electrode, very small gate and very small channel. But here the channel and gate are relatively bigger. So we got a better response for higher concentration. But still you can see the response at lower concentration, the NCR change, the change in NCR at lower concentration here is very high. So that is why we have fitted with the two different line profiles. And here also you can see the responsivity. The responsivity here is somewhere in nanoampere per milligram per deciliter. Remember, in the previous case, we got microampere per milligram per deciliter, but it is the 10⁻⁴ times microampere per milligram per deciliter. So it is almost 4 orders less. The difference here is that we have biased the gate electrode. Here we have not biased. It is not biased. It is simply working as a non-biased gate. Only source and drain is biased. Gate is not biased. Gate potential is simply because of the glucose oxidation happen at the surface. Okay. And that itself is giving the change in while you change the glucose concentration, you are seeing the clear change in slope of this IV characteristics, and you are also seeing the change in NCR values. So all these are only because of the glucose. It is there is no bias at all. Okay, and here also in the amperometric IV curve also you are seeing a stepwise profile, a clear stepwise. In the previous case it was not, but here it is a clear stepwise profile for different concentrations. And once again, this is also not biased. It is simply the reaction happening on the non-biased gate electrodes. And the interference study, once again, we have tested with the dopamine, ascorbic acid, and uric acid, which are the predominant constituents in the in blood, which are the primary interference of glucose. And obviously, these three are not interfering. Only when you add glucose, 100 milligram per deciliter, which is the normal physiological range, it gives a very sharp transformation here. Okay. And the reaction already we have discussed in the previous study itself. But one thing is the H2O2 is forming. So just that is what the mechanism we have seen in our previous study. Now we have to prove this mechanism. How? We have taken three different approach here. One is simply take that electrode and put some H2O2 at different concentrations and see how its open circuit potential is changes. Open circuit potential is nothing but your equal potential of the electrode. Now, if you increase the H2O2 concentration, gradually your potential is increasing. Okay, the positive potential is increasing, and we have fitted that to a linear profile also. So it means that if your electrolyte has more H2O2, your electrode will produce more open circuit voltage. Okay. On the other hand, we also should prove that this H2O2 is coming from the glucose oxidation. That is one important thing. If you remember the reaction, the FAD, sorry, the FAD, reduced form of FAD is regenerated back only when it is getting reacted with oxygen. So in case if I restrict that oxygen, what will happen? So that's what the study here. If I do the experiment in inert atmosphere, my OCB generation is very minimal. But when I do the same experiment in air atmosphere where you have oxygen, you will get a strong increase in OCB. So this tells us that the electrode potential is because of the H2O2, which is generated during the regeneration of FAD. Okay, and we have also proved that with the spectroscopy data. You can see here after adding glucose, you are seeing a strong emergence of H2O2. So all these data tells us the mechanism is glucose is oxidized, and when it is oxidizing, your FAD is reduced, and the FAD is regenerated back by producing H2O2, and that H2O2 is generating the sensing signal. Okay, and this is as per the Nernst equation. When you increase the H2O2 concentration, your electrode potential will, equilibrium potential will change as per this equation. And that's all I have today. And OSCT is a very versatile platform. It is not like our electronic transistor. It's a very versatile platform. You can expose to any environmental conditions. You can put any sample on that, aqueous sample, even organic samples also you can put. You can generate a measurable signal over there. And because of the very high transconductance, the inherent amplification of the amplification of the signal is inherent. So in that case, you will be able to detect very low concentration of some biological or environmental samples if you engineer the OSCT properly. And you can use this device for various applications. We have demonstrated only on biosensing, but you can use it for food sensors, like detecting food toxicants and food adulterants. You can use it for environmental sensing, like detecting some, say, ion concentration, or detecting some pathogens, or even detecting for gases, like the toxic gases like carbon monoxide. You can use OSCTs. You can use it for ECG, EEG probes, okay, because here the gate electrode is very sensitive. Even a small change in potential at gate, the channel current will be affected significantly. So this can be pretty much used as a EEG probe, where there the measurement is the voltage only. On the other hand, you can also use it as a physical sensor, like a pulse sensor and so on. And you can use it as a strain sensor, because when you strain the gate electrode, or when you strain the distance between your gate and the channel, then obviously the capacitance is changing. Then that will give you a very amplified signal. So OSD is, once again, I would like to highlight with a single sentence. It's a very versatile platform. You can use it for a lot of different applications, and all you need is to engineer the platform properly. And with this, I would like to thank you for your attention. And I also acknowledge my institute for the research funding for this research, and the organizers, AFCTE, Atal, and Macet Atal College of Engineering and Technology for giving me this opportunity. And I'll be happy to answer questions if you have any. Thank you.
Participants, you can ask questions now if you have any queries. So, okay. Thank you, sir. It was a really informative and interesting session for us.
Okay, so did I? Yeah.
So on behalf of our institution, Mathanam College of Engineering and Technology, I extend our deepest gratitude to you, sir, for so generously sharing your time, wisdom, and expertise with us. Your session on substrate fabrication and bioconjugation for immunosensors and OECT-based biosensors was truly enlightening, offering not just knowledge, but also perspective and inspiration. We are grateful for the clarity, depth, and practical relevance you brought into the discussion today, from the basics to the advancement of transistors, and especially about OECD transistors. Thank you, sir, for your invaluable contribution to this faculty development program. With this respect and appreciation, thank you once again, sir.
Thank you very much. Thank you all for your time with this session, and have a good night. Yeah. Thank you.
Thank you.
Want that to leave? Bye.
So participants, now it's time to wind up the fourth session of Day 2 FDP program. It is an honor and privilege for me to propose the vote of thanks on behalf of our institution, Marthandam College of Engineering and Technology, at the conclusion of this Day 2 of the Faculty Development Program. I express a heartfelt gratitude to our esteemed speakers, Dr. S. Kiruba and Dr. P. Tamilarasan, for delivering such insightful and thought-provoking sessions. I would also extend our sincere thanks to our management and to all the participants. Thank you for your active involvement and valuable engagement throughout this Day 2 sessions. Once again, thank you all for your presence. And the feedback link is given in the chat box. You can fill the feedback link now.